All right, so we're going to start our part two of identifying and balancing equations, and this is our balancing equations section. Why do we balance equations? Well, we balance equations because we want to obey the law of conservation of mass, which basically says that if a reaction occurs, whatever mass you started with, the products should add up to the same mass. So if you started with 30 grams of product, if you started with 30 grams of reactant, you should get 30 grams of product. And if that's not obeyed, then you're breaking this law of conservation of mass, which says matter cannot be created or destroyed. It can only be conserved, rearranged. So, how do we balance equations? Well, typically we add coefficients in front of our products and our reactants to balance the equation out. You can use any number as long as when you're done that the coefficients are going to have the smallest ratio possible, whole number ratio, and that the numbers that you added are to the front and you didn't add any subscripts. Because as we know, changing subscripts changes what you have as a compound. So no changing subscripts once the skeleton equation has been written. So more balancing recommendations. When you're done, there should be equal amounts of atoms of both sides. So if you have 4 carbons on one side, you would have 4 carbons on the other. If you have 12 carbons on one side, you would have 12 carbons on the other. You should have the same amount of atoms on both sides of each type. And you can use what's called a T-chart. It's not required. I typically tell my students that are just starting to use a T-chart, but it keeps track of your atoms on the left and the right side of the equation. And sometimes using polyatomic ions as a single unit helps as well. For example, if you have 3 phosphates on one side and 3 phosphates on the other, you can typically pull those together as a single element instead of breaking them down into phosphorus and oxygen. All right, so let's say you were asked to write the skeleton equation from what you see there. So go ahead and pause the video if you want to try it, and start it up after that. We're going to say iron is by itself. It's not a Brinkelhoff element, so there's no reason to write a 2. Chlorine is a Brinkelhoff element, so we would write as Cl2. And iron 3, well, iron has a +3 charge. I know that because of the 3 there. Chloride is monatomic, meaning it's one element. Chloride, -1 charge. Do they add up to 0? They do not, so the 3 goes there. So there's our skeleton equation, all done for us. All right, what are some things that we see? We're going to make a T-chart, which looks like a T, showing the total number of atoms on each side, and then we're going to start adding coefficients to balance it. And as you're changing the coefficients, you might have to change what is in your T-chart. So here's what a standard T-chart would look like. So if I look up here, I have one Fe, and I have one Fe on the right. Notice we're breaking down the elements that make up each compound. On the left, I have 2 chlorines. This area down here, you don't have to follow any Brinkelhoff rules. This is all scrap work. In fact, you don't even have to use the T-chart if you don't want to. And I have 3 chlorines on the right. So now I'm going to have to start looking at what's unbalanced. Well, my irons look good, but my chlorines don't. Now, I could put 3 halves here and be balanced, because 3 halves of Cl2 would give me 3 halves of Cl2 would give me a total of 3 chlorines. But I can't do that. I want to use whole numbers. So when you have a situation where there's a fraction would only help you out here, what you need to do is start with the least common multiple of the two numbers you're dealing with. So I'm dealing with 2 and 3. What's the least common multiple between those two? Well, it's 6. So how would I take the chlorine on the left and make a total of 6? Well, 2 times what number will give you 6? 3. And as you're doing that, you're making changes down here. So 2 times 3 is 6, so I crossed out the 2, and I made it a 6. Well, what number do I need to put here to give me 6 chlorines on the right? I have a lot of students that want to try and put a 2 here. But you can't do that. It has to go in the front. You have to unbalance some elements to balance others, but it all works out. So what am I going to put in this position to make that chlorine a total of 6? Well, I'm going to put a 2. And that changes my Fe's to 2 on the right, and it changes my chlorides to 2 on the, to 6. Changes them to 6. Now what's unbalanced? Well, my chlorines are good. My Fe's are good, are unbalanced. Which side are they lower on? And typically that's what you look at when you're trying to figure out what to add. They're lower on the reactant side now, so I know I'm going to have to add something over here. Well, there's a 1 here, so 1 times what will give me a total of 2. Hopefully you said 2. Put a 2 there, and our equation is now balanced. 2Fe plus 3Cl2 yields 2FeCl3. Now again, you do not have to use the T-chart. It's just a recommendation. All right, here's another example. Sodium hydroxide, calcium nitrate. Sodium nitrate plus calcium hydroxide. So we're going to write out the skeleton equation. There we go. NaOH, CaNO3 2, NaNO3 plus CaOH2. Now, if you're having trouble writing these equations, the formulas, you need to go back and watch the PowerPoint overwriting formulas. These are all ionic compounds, so you need to watch the section over writing formulas for ionic compounds. All right, now we're going to make our T-chart. Reactants on the left, products on the right. 1 Na on the left, 1 Na on the right. 1 OH. Now this is what I talked about earlier. Sometimes with OH, which is a polyatomic ion, if you have OH on the left and the right, you can treat them as a single element. So how many OHs do we have over here? Well, that 2 in the parentheses tells us we have 2 OHs. How many calciums do we have on the left? 1 calcium. How many calciums on the right? 1. Now, how many nitrates, NO3s, do we have? We have 2 NO3s. How many NO3s on the right? We have 1. Now, if you wanted to break this down into hydrogens and oxygens and nitrogens, you could. You're going to end up with the same answer. It doesn't really make a difference. So it's up to you if you want to use that shortcut, but I would recommend it as long as the polyatomic ions are on both sides. If they're not, you're stuck. You have to separate it into single elements. So what's unbalanced? Well, the OHs look unbalanced and the nitrates look unbalanced. I will typically start whatever I come to first. That's not always the case, but in this case, I am going to start with the OHs. Which side are they lower on? On the left. So what am I going to put here as a coefficient to make that 2 OHs? Now again, I can't do this. I'm not allowed to do that. That's changing the formula. You can only put something in the front. So what will give me 2 total OHs on the left? Putting a 2 there. Any change you make up here, you have to make down here. So the sodiums, what did they change to? They changed to 2. What did the OHs change to? They changed to 2. Now, my sodiums are unbalanced. My hydroxides look good. But my calcium, my nitrates are still bad. So which side are they lower on? It doesn't matter which one we start with. Again, just start with every one you run into first. Sodium is the one we run into first. Which side is the sodium lower on? On the right. How many do I need? I need 2. Can I do this? No, because now I'm changing the formula. I can only put a number here. I can only add a coefficient. So what I'm going to do is I'm going to put a 2 in front of the NaNO3. That changes my sodiums to 2. What else does it change? It changes the nitrates to 2. Again, guys, placing a 2 in front of NaNO3 is just like writing NaNO3 twice. So how many NO3s do you see? I see 2. So that's why the 2 changes the nitrates to 2. And there's your balanced equation. Alright, so that's part 2 of identifying and balancing equations. We'll do part 3 later on where we'll classify our equations.